Hi, welcome back to another chemistry video. Today we're going to talk about what's called VESPR theory. We're going to be relating our diagrams, so our Lewis diagrams, to this new theory, which has to do with bond polarities. We're going to use this knowledge in order to explain the structure of our molecules, so we'll be looking at molecular structure as well as electron domain structure. And we'll be giving those shapes specific names and also talking about the specific predictable bond angles that these shapes have. So molecular shapes are determined by considering the number of electron pairs around a central atom. When I say electron pairs, I mean both lone pairs of electrons and also bonded electrons. We can also refer to those electron pairs as electron domains. When we have electrons close together, especially when surrounding a single central atom, there's going to be electron repulsion. We have a lot of negatively charged electrons next to each other, so there will be forces between the electrons trying to maximize the amount of space possible in between the bonds and lone pair of electrons. Due to this repulsion, we get predictable patterns in shape. This theory is called the valence shell electron pair repulsion theory, or VESPR for short. So we'll be spending a few days on this theory, and that's because there's a lot of information that you need to know about VESPR. You need to know what the standard shapes both for molecular and electron geometry look like. You're also going to need to know the names of those shapes and the general bond angles associated with the shapes. So there is a decent amount of memorizing to go along with this topic. So basics of VESPR. First and foremost, lone pair of electrons, so non-bonded pairs of electrons, have more repulsion than bonded pairs of electrons. Essentially, they take up more space in our molecule. Another thing that sounds a little odd is we treat multiple bonds the same as single bonds. So we really just think of it as a negatively charged domain. So when we're looking at these Lewis structures, we're really not so much concerned about the number of bonds that are bonded to our central atom. We're concerned about the number of electron domains. So you're going to hear me use that term. So we're going to be counting how many electron domains of bonded electrons there are, and also how many lone pair electron domains. Now the steps that you have to go through in order to actually predict the shape, the first is you have to draw the Lewis structure of the molecule. So it's essential that you are double checking your drawings because you're not going to get the right shape without the correct Lewis structure to start with. You then count the electron pairs, both bonded and non-bonded, around the central atom. And then we're also going to look at the following table. And the table for now is going to help you recall the shape, the name, and the bond angles associated with that shape. At one point, you are going to have to just know which shapes go with which names and which bond angles. And here is that chart. This chart is also available to you in Canvas, which is the chart I asked you to open at the start of the video. Admittedly, this chart looks overwhelming to begin with. The best way to start to quote-unquote memorize is to actually just start using it. I have this separately in Canvas because one, it's going to be larger and easier to read, and two, you can print it off if you want to. But let's take a look at this chart really quick and break it down. So first, like I said, you have to be able to count the bonded pairs of electrons in your molecule as well as the lone pairs. And again, that's going to make predictable shapes. We can see that we have both the geometry for electron pairs, so this is when we actually take into account the lone pairs of electrons on our molecule. And we also have the geometry of the atoms, or the geometry of what I call the molecule, which gives you the molecular model name. Some of it starts to come easily. For example, when you have four things around your central atom, bonded or non-bonded pairs of electrons. It's called a tetrahedral. Tetra means four, so some of this does become second nature pretty quickly. And lastly, it also gives you the bond angles associated with those shapes. It's pretty crucial to know that 180 degrees goes with linear, 120 degrees goes with trigonal planar, 109.5 goes with tetrahedral, bent shape is 104.5, so on and so forth. But these top four right here, I would say, are the most crucial to know. They're the most likely to come up. With that being said, I can't say that these won't show up on the AP. It's just that they tend to lean towards the ones at the top of this diagram. So we're going to draw the following structures, identify the number of bonding pairs and lone pairs of electrons around the central atom, and predict the bond angles, and also name the shapes. I'm going to do the first couple, and then I'll leave the last one for you to try. All right, here we go. So I'm actually going to start with CO2. So if we're looking at carbon dioxide, our first step in order to determine our shape and everything else is to actually draw it. So let's draw the Lewis structure. So we have 4 valence electrons from carbon, 6 valence electrons from oxygen, for a total of 16 electrons. Carbon is our least electronegative. It's going to be our central atom, the one in the middle. If I bond everything with single bonds, I'm going to find that I use 20 valence electrons. We only have 16 valence electrons to start with, so we do need double bonds on both sides of our carbon. And I'm going to fill in our octets, so 2, 4, 6, 8, 10, 12, 14, 16 electrons have been used, and each of our atoms has 8 valence electrons. So our octet rule is also satisfied. Now let's start examining our structure here. Perhaps when you drew it in an L shape or a bent shape. That's fine, but let's take a look. So on our central atom, there's no lone pairs. And we have 2 bonded domains. And this is why I was using the word domains, because you might be tempted to say, oh, we have 4 bonded pairs, which is technically true. We have 4 bonded pairs, but we treat our double bonds like a single bond in this case. So this is really 2 bonded domains of electrons. Now I want to look up the shape in the chart. So let me go pull up the chart. Here's the chart, and I come here, 2 bonded domains, no lone pairs. Should have a 180-degree bond angle, and both the electron geometry and the molecular geometry is linear. So let's go back to our picture. So our electron domain is linear, and I would expect it to match our molecule geometry because we don't have any lone pairs on our central atom. So our molecular geometry should match our electron geometry. Our electron geometry is only expected to be different when we actually have lone pairs of electrons on our central atom. So this is called a linear molecule. This is why I drew it in a line. So when you have a linear molecule, it should have the shape of a line. And our bond angle reflects that linear nature of having a 180-degree angle. So this is the type of information you're going to have to be able to answer about a molecule. All right, let's take a look at iodine trichloride. Go ahead and pause the video and try to draw it. All right, so you should have found that we have 4 group 17 atoms here. So when we count up the valence electrons, it's 7 times 4 for 28 valence electrons. Iodine's our least electronegative, so it's going to go in the center. I'm going to start with single pairs. Group 17 tends to only want a single bond because it only needs one more valence electron to satisfy its octet. Let's see how many valence electrons I've used. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, which means you should have 2 lone pairs of electrons on your Lewis structure for a total of 28 valence electrons. Iodine is breaking the electron domain rule a little bit more later on how to check whether you're actually drawing the right structure for this. But for now, here we go. So we have 3 bonded domains. Right, so 1, 2, 3, and then we have 1, 2 electron domains, or free pairs of electrons. So I'm going to go to my chart, and I see, let's see, I have 3 bonded, 2 non-bonded. And my electron domain takes on the shape of what's called trigonal bipyramidal. And my actual electron geometry for my molecule is a T-shape. And approximately there is a 90-degree angle between each of my pairs of electrons in my bonds. So my electron geometry is trigonal bipyramidal. Ooh, pyramidal. And then my molecular shape is T-shaped. And in between each of my bonds here, I would expect a 90-degree angle. If you have any questions, let me know. Go ahead and try to draw the last molecule right here, bromine pentafluoride. All right, so here's my Lewis structure. I have 1, 2, 3, 4, 5 bonding domains and only 1 free pair. So I would go to my chart. Let's see, 5 bonded, 1 non-bonded. There's the molecule, approximately 90-degree angle in between. Really, we should be drawing it in this shape so you can kind of see the square pyramidal part with our free pair on the bottom. When we have 6 bonding domains, we get an octahedral shape. So octahedral electron domain, and then we have our square pyramidal molecular shape. So there you have it. That's pretty much the entirety of VESPR theory. You have to be able to identify the name of the electron domain, so when we're actually looking at those free pairs of electrons, also the molecular shape, you have to be able to name, and it all hinges on your ability to actually draw the Lewis structure correctly. We're going to be practicing this more in class tomorrow. If you have any questions, bring them to class. Otherwise, have a good day.